pretty much every instruction in this language of eBPF uses registers. So it's like the very basic building block. And okay, so why is eBPF even so interesting from an attacker point of view? So as I said, a user program which does not necessarily have any high privileges on the system can provide a program to the kernel which will run kernel privileges.
Matan, let me, sorry for that one, but let me quickly change the presentation because I think it's somehow the layer below is still ORLs. Okay, so very quickly, let me try to switch between those two. One second. Sorry for that hiccup. But now we'll always be able to maybe go to the right way of the slide that you presented before. 1 second. Let me know when you can actually see the screen.
Okay, yeah, now we see the slides.
Excellent.
Okay,
just quickly going back to that, what is eBPF? Maybe now explain it really fast again, because now finally we can also see the diagram.
So now that we see the chart again, it just says we can see here that there's the right kind of chart that says that shows how we can use it to do packet filtering, and then the left side which shows that it can be used to talk with storage devices like hard disks. So it's very versatile. We can do a lot with it. Okay, let's see where we start. Yeah, this we covered. And
do you have the control?
Yeah, I have the control. Just
excellent.
Okay, yeah, this is where we stop. Yeah, so as I said, a user mode process which can have very weak privileges can supply a program which will run with kernel privileges, meaning that if the user program could do anything with kernel privileges, the entire system is basically compromised. Kernel privileges basically mean the program can do whatever it wants within the system. Basically act as root. This is all within the context of Linux systems. So a weak user can run programs with kernel privileges. So to avoid this kind of faults with the program, there's this part of the eBPF that is called the eBPF verifier. And the verifier has one job, which it has to do very good, which is to prevent these kinds of programs to do things that they're not supposed to do. So access data beyond their context, and write to read from the stacks before anything was written before that to the stack because of again technical reasons. So doing a lot of stuff, but as far as we're concerned, the first point is very crucial: pointer bounds checking, which means basically that if the program has some memory with some size, that it can't do anything beyond that memory. It can't write beyond the memory or before the memory. It can only access the memory that it was given. So again, does a lot of checks to make sure that the program does not act maliciously, that it can do only very specific things, like, for example, as we said, packet filtering. So the only thing it could do is do packet filtering. Okay, so the main focus of this presentation is just seeing how we can go from small, an apparently small vulnerability to something very big, and how an attacker can basically abuse the verifier to achieve this kind of very high privileges. Okay, so here this is a CVE that was found this year. Has a fairly high score, 7.8. Basically meaning this vulnerability can lead to privilege escalation. So again, a very weak user can get very high privileges just because of this specific vulnerability. So the gist of it is that, as we said, there are 11 registers. Again, basically holding data, and this data has some kind of type associated with it. So it can be a number, it could be a pointers to memory, it can be a lot of things. And it has an appropriate type. So, for example, it can be a pointer to a packet. Let's go back. It can be a pointer to a packet, or a pointer to a socket, or a pointer to memory, or just a number. So it wouldn't be a pointer. So it can have some type, and some of those types have the name or null in their name. For example, we can see here there's a pointer to socket or null. Which is basically an intermediate type because some actions can be done which could either succeed or fail. Like allocating memory could fail for some reason, and if it does, it would be null. It will be basically a failed operation, and it's just an intermediate type that could be checked in real time. Check if it's equal to 0, and if so, do something different in the program. But just because it is an intermediate type, it should not have pointer arithmetics allowed on it, because there's no sense in adding numbers, adding values to something that is null. So here the vulnerability itself is that some of those or null types are not prohibited to do pointer arithmetics on. We can see here 3 or 4 types, but some of the types are not here because, again, this is the vulnerability they're missing, and the pointer arithmetics can be done on them. Basically, what we're going to see is how we can go from not just being able to do arithmetics on some kind of data to full-blown privilege escalation. But before we really dive into it, there is one more concept we'll cover, which is BPF Maps, which basically BPF Maps are there to be able to store more data. It's a data structure which can store arrays, hash tables, basically data structures. And it can be used to either store like very large data. As we said, if the program wants to store a lot of data, it can store it on the stack, but the stack is very, very small. So if there's a lot of data to store, it can store it on a BPF map. Or also if the BPF program wants to communicate with the user mode program that supplied it in the first place, it can also do it via the BPF map. So again, just basically a data structure used for communication and for saving data. And basically the way that it looks in memory is there is a map structure which holds metadata. For example, what kind of map type it is, like an array, a hash table, just as we can see in the map types. And there's the map value, which is the actual value stored within the map. Which is right after the metadata. So they're stored one after the other. This is basically eBPF maps. Okay, so originally with every kind of eBPF exploit, traditionally the exploit is if we can get if we have a map value and we can in some sort of way go from the map value and overwrite the map structure, so write back underflow from the map value into the map structure, we can gain a privilege escalation. Very technical process of what exactly we need to do with overriding the map structure, but it's very well documented. It's basically already solved for us. So if we can achieve that, basically going from a map value into a map struct, and writing some things there, we can gain privilege escalation. the very first thing we need to do in order to go back or like go beyond the bounds is basically tricking the verifier. We need some way to make the verifier thinks that we did something which is okay, while in reality we did something that is very much not okay. This is basically true for every vulnerability within the verifier, basically doing something that the verifier does not expect us to do. In this case, again, we can do pointer arithmetics and doing like a series of specific instructions. We can basically get to a point where we have a register, again, just some basically holding a place holding data, which has the value x. It holds any number we like 6, 7, 8, 1000, any value that we like. But the verifier thinks that the value that is actually in the register is 1. And we're going to see why this is very interesting in a bit. But the very first step is already done for us. We just trick the verifier. It thinks we did something, but we actually did something very much different. So great. So we trick the verifier, but how can we actually use that register that has some kind of value that we want to advance our attack, to do something further? So this is what we would have liked to do. Again, we want to go from the map value into the map structure. So what we would like to do is say, okay, we have a register, register 0, point it to the start of the map, and then have our invalid register holding, in this case, x, but we make the verifier think that it's 0. Then if we subtract it, so we started in the start of the map value, then we go into the map structure, and then we can write whatever we like there. This is what ideally we would like to do. But there is a problem with that, which is that the verifier has a part to it that is called LU sanitation, which basically means that at runtime, or even before runtime, because the verifier thinks that our register has the value 0, just like we said, it will make the subtraction to mean actually subtract 0 from register 0. So instead of going back, we'll stay in place. We'll be in the exact same place, and we basically won't be able to underflow. So basically, we have a new problem here, and the problem here is that we can't use pointer arithmetics because again, the verifier just blocks us. If it sees any kind of operation that it thinks it knows the outcome, it will basically not use our invalid register, which is what we actually started with, and without it, we can't really achieve anything. So this is where we basically say we need something else to achieve a similar effect, but without pointer arithmetics. So there is this concept called BPF helpers, which is basically some functions that any BPF program can call to do various things, like generating random numbers or getting the current time and many more, as you can see here. So basically just extend functionality for ease of use of the program, or even do some things that the program itself can't do very easily. So basically just extending functionality, and as it appears, there's a couple of functions. This one is an example. There's a function called BPF skb load bytes, which basically it's just a function that is used to read data from a packet to memory. So again, it's a packet filtering program. It can just use a function to read data from a packet. But if we use again if we put here our pointer to the eBPF map, and for the length we use our invalid register, which would be a very big length, bigger than the size of the map, we could then overflow it. It is important to note that the verifier normally would block us, because again it does do some bounds checking. So if it just sees a very large number, it would block us. But in this case, because again we have a register which the verifier itself thinks has the value 1. It would think that the operation is actually within bounds. It's just copying 1 byte as far as the verifier is concerned, even though we did provide a very big number. It could be 1,000, could be any number we want. Okay, so this is what we achieved so far. We have a map value. We can load it into the register, into one register, then add our invalid register, go beyond the map value. So we have an out of bounds read and write. Another function can actually give us a read primitive. So we can read or write beyond the map value. So that's great. And how can we use that now for a final step to just, as we said, overwrite the map structure itself? So as we said, this is what we actually wanted from the start. We wanted to go from the map value and go back into the map structure and overwrite some things there. But what we have is we actually are able to read and write beyond the map value. So not backwards, but forwards, which is not exactly what we wanted. But what if we could do the following? Just have 2 maps, one after the other, and then we could just, again, a struct followed by a value, then another struct followed by another value. So if we could just do everything from the first map, we could actually write into the second map structure. So this would be amazing. If we could do that, it would basically be done. There is one problem with that, which is that if we allocate 2 maps, if we generate 2 maps, it's not guaranteed that there will be one right after the other. There could be a lot of junk in between. They could be very far apart. So we need to find some kind of way to make it so that that if we keep allocating them, at some point we need to know if they are one after the other. So there's one thing that we can do. Again, a map value is something that the program controls. It can put whatever value it wants in there. So what we can do is just generate a lot of maps and give each map a unique value. One will have the value 1, for example, another will have the value 2, just any unique value that doesn't collide with any other map. And just if we keep allocating them over and over, basically at this point, okay, if we read from map value A and we use our out of bound reads, we basically won't see anything interesting after it. It will be, again, this junk. Same for value B. There's nothing interesting right after it. But if we keep allocating, in this case, we allocate map with a map value C, then we can see that, again, map value A and map value B, if we read from them, there's nothing interesting, but reading from map value C, if we read enough memory, we'll actually find map value B. So in this case, we can know for sure that we have actually successfully have 2 maps that are one after the other, and we can freely do our override. Yeah, so yeah, at this point we can just override it. The actual steps that need to be done with regards to what exactly we need to override. Again, very technical thing. It was in an article that was published by a researcher called Manfred Paul. Very interesting article. Feel free to read it. Very interesting, but a little too technical for now. But again, very well documented. And at this point, if we get here, we have a privilege escalation achieved. Okay, yeah, shouldn't say about me. So here we have a little demo. See if we can start it.
Is it a demo? Can I try to run it from my side?
Yeah, go for it. Can start it.
1 second. I cannot see the play for it. 1 second, let's see. second. Okay, let's reshare it. Let me know if you can see it.
Yeah, looks like we can.
But for some reason, it's not. No, it cannot play it for some reason. No idea why.
Okay, well, we can skip it. But
later on, we will share it with you guys.
Yeah, great. Basically, what's in the demo is we could see just like starting the exploit, and then it shows that it allocates various maps, 2 maps at a time, basically, and then generating unique values for each of the maps. And then at some point, it encountered one of the maps that was previously allocated was right after another map. So basically, it knows that they were one after the other, then did some of the technical stuff that we talked about. And basically, we got to route this way. Yeah. So pretty much to conclude, we can go back to the presentation, right?
Wait 1 sec.
Yeah. Yeah, okay, so
remote control again.
Great. Yeah, so just the conclusion is again that we started from a very small bug, just like in appearance, just being able to do some kind of arithmetics on a register that we're not supposed to, which to an untrained eye might seem like something very irrelevant. Like why is that something that could actually bother me? And step by step, an attacker can get from this very small thing to an entire compromisation of a system. And also we saw a new technique for this to achieve this map structure override using map value overflows, which again previously it was used in map value underflows. So just a new technique that could be used with any kind of vulnerability that achieve this, and not just this specific vulnerability. So again, a very interesting technique, and that's it.
So thank you very, very much, Matan. So couple of questions. I'll quickly go to the questions with you, and then Uriel, don't skip. We still have a couple of questions for you as well. So someone asked here, when you're using only Linux in the demonstration, or basically you need also other tools. So if someone wants to reproduce it.
To reproduce it, first of all, there's a POC that we have in our GitHub for this particular exploit. So basically, to reproduce it, if you just want to check this, you can download it, run it. It's supposed to be very simple. All you need is a Linux system that is vulnerable. So it is limited to a subset, like just Ubuntu and some versions of Ubuntu, but yeah, not a lot of tools are needed. Just basically compiling a C project and running it. That's it.
Mm-hmm. Now, another question that I received is, so basically what you presented here an issue, you hardly presented, a way maybe to countermeasure it, or, what are the best ways to avoid such writing eventually to the memory. So what should be the way? Is there an issue of the architecture with, new type of vulnerability, etc.? So we basically need to restructure the architecture of the kernel in this case, or there are other ways to solve it?
Okay, so basically, the best thing that can be done is keeping your systems up to date, because as soon as these kinds of vulnerabilities are reported, there's already fixes for them, which is already pushed into the GitHub. So all you need to do is keep your systems up to date. This is the very basic thing. But of course, if a vulnerability is there and it's not really reported yet, what can you still do? So specifically with eBPF, there's actually an option to not allow unprivileged users to run programs at all, which is what should be the default. It's now the default in most cases. Just in some cases it's not. For example, in Ubuntu 20.04, back when this vulnerability was out, it was not allowed. I'm sure. I think today, or it was allowed back then. So low privilege users could run eBPF programs, but I think now they cannot. But basically, this mitigates any kind of eBPF privilege escalation vulnerability, because if a user cannot run an eBPF program, it cannot exploit the eBPF subsystem.
Okay, thanks for that one. And another question is there a trying to understand from a really long question someone asked, is there something to in the future, are you going to enhance that research? Are you going to show more capabilities around that area of accessing memory? Is there something to look up for besides the existing research that you already published?
Yeah, of course. I mean, whenever there's some kind of interesting vulnerability that is either reported or that we find one, for sure we investigate it and try to maybe exploit it, or just see what the attack surface regarding it is. So there is not something very specific in mind right now, but whenever there's something interesting, we're working on it for sure.
You will publish it. Okay. Thanks a lot, Matan. Thanks again for the presentation. Going back to you, Matan, Uriel, I saw that you already answered in the Q&A section. So just in case some people missed it, take a look at the Q&A. But I either way quickly go through it just for the sake of those that maybe missed it and are still with us. So Kobe asked, what will be the best protection against ransomware attacks? And Uriel, you answered that more telemetry data, obviously with better detection logic. So basically, knowledge will be the solution, like everywhere for that sake, and maybe the concept of sharing data, etc., will obviously help. And also, you provided with a link to your training workshop and services for Wissam that asked about if you can share recommended courses, etc. I assume, by the way, that you also asked for more recommendations besides just yours. I'm not sure if that in that link you had some other ideas or recommendations for things that besides yours, for example, I don't know, other courses in other websites or something like this. But guys, go check out. So just to summarize it, and I hope that you all enjoyed today's session and you managed to learn a lot from the sessions that we had today. So just to remind you all to track the meetup, because we will upload the recording. So you'll be able to hear again Omer, you are going to live forever by that recording. You will be able to hear Omer from Enzo Security, explaining the concept of code OS, or what are the risks in your IDE, in your environment of development. You'll be able to relive Uriel's cool stuff about red teaming, blue teaming, and why it's important to eventually share data, and always try to think with the right edge on both sides. Try to think as the attacker, try to think as the defender, and try to combine those, because we all know that the strengths of all of those two things together obviously is much more stronger than one of them only. And thanks again, Pantera. Thanks again, Matan, for presenting the good, bad, and the compromisable aspect of Linux eBPF. it was really, really refreshing to look at, we sometimes look at, vulnerabilities, very specific things, and we forget that there is a huge architecture behind it that, exists for the last, 10, 20, 30, 40, maybe even more years, especially in Unix, for example. And some of those things are, just inherited. We got those as is with their own malfunctions or with own issues. So thank you, everyone. Thanks again. The recordings will be there. And of course, register to our meetup. If you are not members of our meetup, that's a good opportunity for us now to ask the guys here on the call to attack you just because of you are not members. If you don't remember how to register, let me quickly share that one with you. And one sec. No. Something happened today with all the presentations.
We send the link to our meetup group in LinkedIn. So in the chat.
Okay.
Please join.
So again, in the meetup, yes, thanks a lot, Leo. And again, in the meetup, we always bring more and more ideas, more and more capabilities. Some of the members here already mentioned, it's not the first time that they are presenting, and it won't be the last time. There is a lot to look out for. See you in the future, and we will share again, as I mentioned, in the meetup, the recording of today and a few other meetups in the next future. Thank you, everyone. Bye-bye.
Bye, everyone.
Bye-bye.